Hello, my name is Ron Larson, and I'm delighted to be able to tell you about our work on characterizing the rheology, slip, and velocity profiles of lamellar gel networks. This work was carried out primarily by Anukta Datta and Tanmay Velandanda, two outstanding master's students, as well as my PhD student, Grace Tan. This was done in collaboration with Sumant Jamandagni and Jeffrey Reynolds of Procter & Gamble Company. And that company also generously supported this research work. Hair care conditioners are creamy lamellar structures that are formed by mixing a couple of fatty alcohols, in particular cetyl and stearyl alcohol, together along with a long chain cationic surfactant. The reason for choosing two fatty alcohols is to block or frustrate the formation of a crystalline phase, which can lead to the separation of water from the mixture, as shown here. So with the presence of both fatty alcohols, you get a nice creamy mixture instead. So as shown by simulations, as well as known to occur in experiments, at high temperatures, these materials form an L-alpha phase, which is a bilayer with disordered tails. That as you lower the temperature to the reduced room temperature, the tails order up on a hexagonal lattice, as shown by this particular view of the simulation. And in excess water, and these systems have 85 to 95% water, you get a network of these lamellar phases producing the creamy kind of rheology that's observed in these systems. So we've studied the rheology and also imaged the shear flow using a cone and plate rheometer and viewed the sample from the side using a camera and a lens. And this equipment was donated generously to us by Anton Parr. So first of all, let's look at the flow curves. Here we show this in the form of stress versus shear rate on the left and viscosity versus shear rate on the right. And you see high shear thinning in these materials with some reproducible bumps in the curve. When stress is plotted against shear rate, you see a decrease in stress as a function of shear rate with a local minimum. And this is thought to not be observable in materials because of the formation of shear bands, which should occur when you have a shear stress that decreases with shear rate. And when bands appear, you should see a flat line, constant shear stress as a function of shear rate, with the shear rates at the endpoints of that line being the shear rates in the bands that form. Now we can understand this behavior better by looking at a hysteresis loop, where you see that after reaching a maximum shear rate, if you then reduce the shear rate, this local minimum in stress goes away. So in fact, the local minimum here in stress is due to some kind of shear-induced restructuring of the fluid. And we find that if we repeat the hysteresis loop, then the new loop basically falls on this lower shear rate curve, this lower curve of returning shear rate. Now, if we repeat the hysteresis loop, but for increasing shear rates, we find that the lower branch of the hysteresis loop is actually set by the highest shear rate that was obtained in the experiment. It takes some time for the material to recover its original properties, but if we wait up to 12 hours, you can see the second hysteresis loop begins to recover that of the first one. So it's a very slow healing material once it's been sheared. Now, if we apply a constant shear stress in order to measure the creep behavior, we see two kinds of behavior. One, at low enough shear stress, below about 18 pascals, is a solid-like or quasi-solid-like response, with strain increasing with time to the 1/4 power If we exceed critical shear stress, then we get a much faster, more fluid-like creep with strain going as time to the 1.35 power. We see that the transition from the solid-like to the more fluid-like creep is coincided with the disappearance of recoverable strain after you stop the shearing. So the fluid-like structure does not have any significant recoverable strain. Now, if we perform a step strain, we see a very interesting, simple power law response with modulus decaying as time to the -1/4 power. With reduced strain, we recover what appears to be a linear viscoelastic regime when the strain gets to 0.5% or below. So then we might expect a similar power law in oscillatory shearing at low enough strain, but in fact we see something quite different with behavior very different from the expected power law. Now, we might suspect this is due to some nonlinearity, but if we do a strain sweep, we find that nonlinearity only sets in at strains of around 10%. And so, in fact, we should be in the linear viscoelastic regime in the G prime, G double prime measurements. So then it's a puzzle as to why we don't see the same behavior that we saw in the step strain, because the two should be related to each other through a Kramers-Kronig relationship or through typical linear linear viscoelastic transformation functions. So the answer to this puzzle, we think, is due to banding that forms so easily in these materials. And this is illustrated here in this example, where a shear rate is able to generate the band formation. So if we look at this more carefully, we find that bands form even at very small shear rates, 10 to the -3. You quite quickly get the formation of a band, two bands actually. And for even slightly higher shear rates, 10 to the -2, the band becomes a plug, which simply all the material just slides as a solid block at a velocity that's some fraction the velocity of the moving plate. And this behavior continues for higher rates of shear. So from this, we might expect that this material is behaving essentially like a solid, and so its stress should be essentially sliding friction or tribological in nature. And so as long as the velocity of sliding is the same, one might expect the gap not to matter. So we can test that by using different gaps between flat plates here in these experiments at a fixed velocity, but we do not find the stress to be independent of the gap. It is gap dependent. So the simple alternative to this would be what we might call rheological behavior, where what matters is the shear rate, not the gap or the velocity. But if we plot stress versus time at fixed shear rate but different gaps, we also fail to see superposition of the data. So the curves are in inverse order here. So this seems to show that our behavior is somewhere in between tribological and rheological behavior, somewhere halfway in between these two. So this makes the material challenging to model, but perhaps one model that might show promise is the so-called soft glassy rheology model, or SGR model, proposed by Solich, Cates, and co-workers some time ago. And this model shows a number of the features that we see in our rheological measurements, including the hysteresis in the stress response in up and down shear ramps, the appearance of shear banding, a logarithmic solid-like creep response below some kind of a yield stress, gradual stress decay following a sudden shear strain over a wide range of timescales, and a storage modulus that significantly exceeds the loss modulus by an order of magnitude at least. And so this gives us some clues as to what direction to take to try to model these quite complex and interesting materials. So I'll stop there and again, thank those that did the work. And this is from a picture of the Larson group. And want to also acknowledge some interactions or collaborations with Sarah Safina from UC Santa Barbara. Thank you very much.
Recording has stopped.